All right, so in this question, basically you have to push arrows to prove why one of each pair is more acidic than the other. So if you take a look at the first pair out here, you have a nitro group connected to a phenol at the para position, and then out here you basically just have a blank phenol. Okay, so the key to understanding or really trying to uh, figure out why one molecule is more acidic than the other is to first remove a proton from the most obvious place and write out the conjugate base, okay, and then see how much resonance is in the conjugate bases. If there's more resonance stabilization, that means the conjugate base is more stable. Okay, so if you write out the conjugate base of the first compound by deprotonating the OH, and it's always good to draw out all the groups, okay? And then compare that conjugate base with the conjugate base of the phenol. Notice carefully, the negative charge can be delocalized in the ring in both cases. However, in the first case, this can go into the nitro group because the nitro group is electron withdrawing. Therefore, the nitro group at the para position actually increases the stability of that negative charge. Therefore, in this case, this compound is going to be more acidic. Okay? All right, take a look at the next one. In this one, again, we're going to adopt the same strategy. We're going to draw out the conjugate base. So I'll just, since both of these are OHs, I'll just pull out one H, keep the other OH intact. And in this case, in the case of this one, again, I'll pull out that, but then the CN is a different group, so I have to write it out like that. And the second I write it out, I can notice that's an electron withdrawing group. So as you can see, if I delocalize the electron, see how it goes into the CN at the para position? And now if I compare the same effect out here, it cannot go into the OH. And the reason for that is because the OH has its own lone pairs that want to delocalize into the ring. So if I kind of use like a different system of arrows, as you can see, the arrows kind of clash against each other, whereas in this case, it just goes one way. Therefore, this conjugate base is more stable. Therefore, this one is the more stable, is the stronger acid. All right, now let's take a look at this one and this one. In this case, the only difference between the two compounds is that the SO3H is at the meta position to the OH, and as opposed to out here where it's para. So again, if I draw out the conjugate base in the first case, I'm gonna draw the arrows a little differently so I can draw the. I'm going to put the SO3H on the other side. It shouldn't matter, and I'm going to draw it out so I can understand what's happening. And then out here, I'm going to show the delocalization. Actually, I'm sorry. I should have put I'm going to just change the arrows in the ring so that it's a little easier for me to show you what's happening. Okay, so there you have it. Now that arrow goes there, that goes there. But see, in this case, once this double bond forms out here, then this arrow is going to jump over. So basically, the electrons out here, it actually jumps, it goes by the SO3H. It doesn't really get a chance to delocalize into the SO3H. Now compare it with this situation. Let me change my colors. Here's my conjugate base. And there is my SO3H. And when I start pushing the arrows, that goes in. and that goes up. See, electron withdrawing group at para position is making the conjugate base, or rather stabilizing the conjugate base. Therefore, in this case, that is a stronger acid. If you again look out here, the only reason the SO3H couldn't stabilize the conjugate base is simply because the electrons do not delocalize into the meta position. They're only going to go either to ortho or para. And since the group wasn't there, therefore it couldn't affect it. Now let's take a look at this one, D. D is a very interesting case because you have the NO2, and as I just mentioned, that the electron withdrawing group needs to be at ortho or para. It seems that in this case, it should be the same. But let's take a look. And you have to think about this a little differently, okay? So in this case, this kind of follows a very similar strategy to what we did up here. See, there was the conjugate base, and I'm just going to copy that and put that down here, okay? So there it is, 1, 2, 3, 4. Okay, completely stable. And then look at what happens out here. You would, if I draw the conjugate base for this one, there it is, and then you have NO, O minus plus. That can go there, that can go there, and that can go up. So if you compare the effect out here with this here, it's not very different, right? It's the NO2 is still withdrawing. So then how are you going to figure out which one's a stronger acid? So the trick out here is that turns out before the proton before the proton comes off, if you redraw the structure out here a little differently, you'll actually see that the proton faces many challenges before coming off. So I'm going to draw this out so you can see the challenges it faces. So when I drew out these two forms, notice carefully, there's actually an intramolecular hydrogen bonding. Intramolecular hydrogen bonding that takes place out here. And this form is actually notice carefully, that forms its own little 6-membered ring state, which is actually what it likes to be in. We already learned 6-membered rings are very stable. So this hydrogen, it wants to come off, but it's not allowed to come off as easily because this oxygen wants to grab onto that hydrogen via a hydrogen bond, okay? Therefore, in this case, because the hydrogen cannot come off that easily, this one's going to be a weaker acid, okay? So therefore, this one's the stronger acid. All right, and then the last one out here, you have the OH and you have this group. Again, this one's very similar to the SO3H one. If you draw out the forms out here, you will actually see that this one's actually this one's an electron withdrawing group. So let's draw out the conjugate base. And again, this one is an ester. If I draw the electrons out here, see how it jumps over? It jumps over the group, so no chance of that group stabilizing the conjugate base. But if I draw this, see, it sucks it in. Therefore, this is a more stable conjugate base. Therefore, that is the stronger acid.